In order to output a sinusoidal signal, it is required to calculate the value of the voltage at several time points during the period. So each of the time points represents a sample, and the accuracy of the sinusoidal waveform is improved by having more samples per period. So the frequency of the waveform is determined by controlling the delay between outputting each of the samples. So this time step dt is equal to the total period t divided by the number of samples, or we can reorganize that in terms of frequency, because obviously frequency is just a reciprocal of the period. So we need to control, by controlling dt, we can essentially control the frequency of this signal. So we'll look at this waveform here. So this is you can see this is a kind of sinusoidal waveform made up by the discrete points. So remember that these points only exist on these kind of vertical lines. These lines are just joined, are just the kind of guides to the eye. They're not, these are the only samples. So we've got samples 0 to 15. So the total period is t, and then this is the time step dt. So it's worth noting here that period, the end of the period doesn't end at 0. So the period starts at 0 here. But the end of the period is one sample before that. So this, when we go back to 0, that'll be the first sample in the next period. So the actual period itself is just made up of this part of the waveform and not this part. So when the next period starts, that again will obviously start from 0 then, and we'll get the correct waveform. So we've got the total period divided by the number of samples will give us the time step needed. So there are maths libraries available in C and C++. We can calculate, the value for a given time step. We can calculate the value of sine using the sine function, or cos or tan or whatever. But trigonometric functions are computationally expensive in terms of CPU clock cycles. So if you want to keep outputting a sine wave, you don't want to keep having to calculate sine or cos inside of a loop, because it takes quite a few clock cycles to do this calculation, so it can slow down your code. And because obviously it's a periodic waveform, you actually only need to calculate these once. So we can actually just calculate the values for one period and then save them in the array, and then later, so the array then is stored in RAM. It's much quicker to fetch data from RAM rather than calculate the values using a trigonometric function. So we've got all our values in an array for one period, and then later in the code we just retrieve the values from the array rather than recalculating. So when we use an array like this, we tend to call it a lookup table, or LUT. So you see LUT, that means lookup table. It's much more efficient in terms of CPU cycles to fetch data from the array or from RAM than have to recalculate. So in this example here, we'll define pi and n as being the number of samples. Then we've got an array. So this is a floating point array of n samples long. We've initialized them all to 0, and it's going to loop through once. So we've got a for loop. It's going to loop 0 up to I less than n. And for each one, it'll calculate the value of sine at that point. And, well, it's also got this printf here just so we can debug and print the messages. So after we've done this, we've only had to do, 16 in this case. We've only had to do 16 sine calculations. And we can just store the values in y, and later on we can just use the values stored in y in the DAC. We'll just mention memory constraints, because each element in the array takes up a particular amount of memory or RAM, depending on the data type. So both ints and floats are 32 bits, so that's 4 bytes. So if you've got an array, so this, for say 1,000 elements, it's not unreasonable. That's going to be around 4 kilobytes of RAM. Now if you consider the NXP LPC 176J has just got 32 kilobytes of RAM. That's quite a big chunk of memory taken up just to store an array. So you've got multiple arrays and so on, like you do in some applications. It's very easily possible to use up all the available RAM just in arrays. So, in fact, if you create an array whose values don't change, it's actually possible to store it in flash over RAM, and we do that using the const keyword. So we can see this, the same microcontroller, it's got 32 kilobytes of RAM, but it's got half a megabyte of flash memory, so it's much more flash than RAM. So if we can, it's better to store arrays in flash, but they need to be constant arrays. So in the previous example, when we use a loop to populate the array, that we can't do, that's a dynamic array. So if you're going to create a lookup table like this, you'd have to calculate the value, that the signed values offline, if you will, and then manually put them in the array. So in this example here, I've just got this global variable now, global array for this array, and I've put this const keyword in front of it. So when the compiler compiles it, it'll now get all these values, what we've defined here. So these values are for the signed values, have been calculated offline, and then we've been initialize this constant array with those values, and then the compiler will put that in flash rather than RAM, so it's going to free up space in RAM, and it'll just use with flash, we've got much more memory. So later in our code we can just use this array as normal, so just looping through this array, printing out the values, but now that array is stored in flash rather than RAM. So this is very useful. So if you've got an array what can be constant, or strings what are constant, put the const keyword in front of it and put it in flash rather than RAM.